Very good morning to one and all present here. My name is Dr. S. Dinesh Mohan, Associate Professor, Department of Pharmaceutics, VIPER. I will be giving the introductory speech for today's resource person, Dr. Soumya Sasmal. It is indeed a great pleasure to welcome you, sir, on this one-week faculty development program of recent advances in science and technology innovations. Dr. Soumya Sasmal graduated from the University of Jodhpur at Kolkata with a Master of Technology in the year 2006. He received his PhD in Chemical Engineering from the Indian Institute of Technology, Guwahati in the year 2014. Dr. Sasmal joined as a scientist at Nagarjuna Fertilizers and Chemicals Limited, Hyderabad in 2006. Later, he joined in a Center of Innovative and Applied Bioprocessing at Mohali as Scientist C in the year 2013. At present, Dr. Sasmal working as Assistant Professor, Netaji Subhas University of Technology, New Delhi. Dr. Sasmal published more than 20 research papers in both international and national journals and holds 2 patents. Dr. Sasmal wrote the book chapter entitled The Biological Messengers and Its Kinetics, Modern Biotechnology and Its Applications. We are greatly honored to have you, Dr. Soumya Sasmal, to present the plenary talks of current and future trends in second generation bioethanol production. Please join me in welcoming Dr. Soumya Sasmal. Over to Dr. Soumya Sasmal. Thank you, sir.
Thank you, sir. Thank you, Dr. Dinesh. Thank you for your nice introduction. So, first of all, good morning to all of you. Respected Chairman Dr. A. Ramesh, Principal VIPER, and co-chairman of this all this event, Dr. O.N. Tiwari, Principal Scientist, IRI, New Delhi, and also the convener, Dr. K. Vanita, HOD Pharmaceutics of VIPER. So thank you. I would like to send my sincere greetings to all of you, and also give me an opportunity to discuss my research thoughts and whatever I have published and whatever I am doing the research in this event. Recent advances in science and technology innovations organized by your Vishnu Institute of Pharmaceutical Engineering and Research, Hyderabad. So in my introduction, already Dr. Dinesh told me that my career has started in Hyderabad and in Nagarjuna Fertilizer and Chemicals Limited. And at present, I'm in New Delhi, which is also Dr. O.N. Tiwari. I'm really thankful for that he is inviting me. And that is in Delhi. So both these 2 places in my heart, and it will be remain in my heart. So I have started my career in working in bioethanol production only, and still I am going on this thing. So I choose this topic without any second thought that what is the current and future trends in the this second generation bioethanol production. So enter my talk, I will discuss what is the current thing is going on and what are the future trends. Future trends in terms of what we academicians, we scientists are thinking, and what will be the implemented in future. And why second generation biofuel, not the first, third, and fourth, that also I will explain. Especially I'm working on the second generation biofuel almost last 14 to 16 years. So this kind of thing I will discuss. So I hope this is the third day of our this FDP. And this entire day, I think so many distinguished professors and scientists, they have discussed their own opinion, and all people have enriched. So I think this talk will also help the student, whoever, even the faculty, whoever is there, listening this, to they will also enrich their research knowledge. So I will start from vision. So why I am thinking on this bioenergy, bioethanol, biobutanol, and those kind of things. So first, I'd like to show you that why and how we can get the energy. We know that whenever we are working anything, or the civilization started, the demand of energy is increased. So if a highly civilized society means high amount of energy is also required. So how we can deal with that? So till date, we are depending on nothing but your fossil fuel based energy. So this fossil fuel based energy, basically we are calling this as a black energy. So huge amount of hydrocarbons we are utilizing, and after doing in any kind of business in terms of agriculture, in terms of our any other kind of activities, let's say for transportation and other cases, every time we are using this kind of black energy, and it emits carbon dioxide and other greenhouse gases. And what is the resultant? Resultant is the pollution. That is very well known. So the next mission is that to how can recycle these gases, especially the gases. It's not that there is a misconception that if we are using biofuel, that there is going to be no pollution. No, pollution is there. It will also emit the carbon dioxide and other COX and NOx gases. But problem is that, or I can say it's also one kind of opportunity that if the carbon dioxide, whatever it is generated, we can say if we do the life cycle analysis of those kind of biofuels, when it called compared to our hydrocarbon things, this carbon dioxide, again, with the help of solar energy, again, our plants can consume that. So that's why when we are discussing about the life cycle analysis, we can say this biofuel, these are very environmental sustainable and it will not give any pollution. So this misconception of that biofuel won't emit any carbon dioxide, or it is not suitable, it is very good for our environment, it is a wrong concept. When we're doing the life cycle analysis, again I am repeating it, then only I can say there is no pollution of that. So what is the key driver or business vision of this entire thing? So the key drivers are like global warming. It's due to the emission of this COX and NOx gases, and irrespective of our the more we dependent on this kind of fuels, obviously the global warming will be there. So if we again started our biorefinery concept or utilizing the biofuels, then chances that this global warming we can little bit reduce, because the carbon dioxide and other gases, whatever it will emit, it again captured by our the energy crops and whatever the biomass is supposed to use it. And the world energy demand, definitely we are going to more civilized, and more civilized nation means they will utilize more amount of energy. So you have to utilize this kind of energy in a sustainable manner. So that's why that is the important driver. Another is the feedstock availability or the sustainability. We know that although we are saying that diminishing green colors, that is we are utilizing the forest and other things, but still when you are doing the cultivation and the forests are there, so feedstock availability is also be there. So if you are cultivating for this biomass materials, like the lignocellulosic biomasses, in terms of energy crops, in terms of forest residue, anything, so that feedstock availability will be there. In terms of there is some geographical limitation depending on the geographical area, we can cultivate different kind of biomass, and we can easily utilize those kind of biomass for biofuel generation. So another thing, two things are important. There is cost competitiveness and the process and technology advances. So cost competitiveness, it will always compete with our fossil fuel technology, and obviously if we can improve on new technology, this technology will definitely, it will be low cost and it can easily compete in everywhere when we are competing with the fossil fuel based thing or fossil fuel based energy. So the business vision means why the any whatever we are doing research today, at the end it should be helpful for our community. And the community means some big organization, even the startup organization also, they can do some business, which will be basically translation kind of thing. So why and how they can do this? So it's not that they will only create the biofuels or in terms of ethanol or in terms of butanol or in terms of hydrogen, but they also produce some chemicals that we can say the green chemicals. So whatever the chemicals at present we are utilizing in our laboratory or in our day-to-day activity, most of the chemicals are basically derived from the petrochemical industry. So if we can replace that kind of thing, and those kind of chemicals we can produce, yes, I emphasize this term, we can produce it from these biomass materials, then it will be very profitable business also. So apart from the chemicals, fuels are already, today also I will discuss it. And obviously we can use unconventional feedstock. So this feedstock means nothing but the green biomasses or the lignocellulosic biomasses. So there are various kind of conventional biomasses are also there. Let's say for corn, if we produce corn, it's a very conventional things, but unconventional things are also there. If we explore more kind of biomasses, which is available in our area also, depending on different geographical location. Still, I can recall when I was in Hyderabad, again, I am also worked in that this Medak district only, where the VIPER exists now. So I am really amazed when I become a little bit can recall those days, 2006, when I'm working in the Nagarjuna fertilizer in Medak, the laboratory, Nardi. So they are working on the sweet sorghum biomass. So in that region, that sweet sorghum is much more popular. Later, when I shifted to Guwahati, in that region, cultivation of energy crop was not that much, but huge amount of forest residues are there. And more amount of this kind of thing are areca nut husk, moss, and those kind of biomass. Then when I again visited to the Mohali, Punjab region, there I can found huge amount of rice straw, wheat straw, those kind of things. So when the geographical location is changed, so biomass material will also be changed. So that's why I can say the unconventional feedstock depend on its geographical location. So before starting, I would like to also say why I will emphasize on the bioenergy. So if I will find out what are the sources of energy, I can find the nuclear fuel, that is the most economical, and I can say the pollutionless fuel after the fossil fuel. So why? But nuclear fuel has a limitation because it needs a sound energy, need a huge amount of good kind of places, and sometimes it also is susceptible for pollution in terms of hazard. Yes, it's hazard. We are not forgetting the Chernobyl incident in Russia, which happened in 1980s. So if such kind of thing has happened, then a huge amount of loss will be there in terms of environment, in terms of human, in terms of animal, everywhere. So that's why people are still, some political issues are also there to implement the nuclear fuel energy plant. So if I'm not looking at the nuclear fuel energy, other sustainable energy or some renewable energy concepts are there. So that's why those kind of fuel falls under non-fossil and non-nuclear fuel energy. So this kind of energy falls like wind energy, solar energy, tidal energy, hydro energy, geothermal energy, and biofuel and bioenergy. So if we have a look at this kind of thing, so wind energy, solar energy, these two energy are basically very highly sustainable. That means we're supposed not to worry that how nature will replenish that. If we utilize it, it will never end. But problem is, again, it's a geographical limitation. We will not get the solar energy or wind energy in everywhere. You can find wind energy in India, especially in the Gujarat or the Tamil Nadu region, but you will not find in the West Bengal, even in Delhi region, you will not find the wind energy. Same way for solar energy, you will find Rajasthan area is much more better than in other places. So that's why it needs a geographical limitations. Again, the tidal and hydro energy are also have the similar kind of thing. And last of all, the geothermal energy. Some people are claiming that it's also one kind of fossil fuel energy, but few people are also claiming that no, it's not a fossil fuel energy, it's also one kind of a renewable energy. In Madhya Pradesh region, you will find some region in the Narmada Valley, the geothermal energy. It's a huge amount of heat, we will collect it and we can easily transfer it for the other form in terms of electricity, in terms of liquid also you can make it. So again, it has some geographical limitation, but except this biofuel or bioenergy concept, because cultivation is everywhere. Let's say, I can say this agricultural lands are everywhere in India. Almost 70 to 80% people are, their livelihood depends on their agriculture. So biomass, and I can say that especially the lignocellulosic biomass, it's available throughout the India. Not only the India, even throughout the world also. So everywhere anyone can implement the biofuel or bioenergy plant. Even it does not require that much of skill if you would like to put in the nuclear fuel. So in future, obviously it will compete with the nuclear fuel and the biofuel or bioenergy. And I am sure that bioenergy, this will win the race. So the plan of that biorefinery. So traditional concept was there. So traditional concept was there that from the fossil fuel based energy, we can easily produce some other chemicals. So if we replace those kind of fuels, fossil fuels, that means the petroleum based fuels, instead of biomass, in place of biomass, so we can make a biorefinery. So petroleum refinery can be replaced with the biorefinery. There are two platforms. One is a sugar platform, another is a syngas platform. So the sugar platform, basically, it is a biochemical route, whereas syngas platform, there is a thermochemical route. So this sugar platform, basically biotechnologists and other biological students and those kind of people are handling, whereas the syngas platform, it's a chemical engineering field, those people are handling. So nowadays, there is no limitation. Anyone can do anything if they gather the knowledge. And if we get the sugar platform, we can combine heat and power also. And after doing fermentation, or we are doing the gasification and pyrolysis, these two routes, finally we can get some fuels, chemicals, and other materials. So that is the concept of biorefinery. So this is the biomass and few attractive feedstock. Why we can assume that biomass is an attractive feedstock? First of all, it's a renewable resource. That means easily we can replenish it. Second one is it's a positive environmental properties. That means after making the ethanol or the hydrogen, whatever the biofuel, you can make it, even the syngas and other things. Easily this kind of carbon dioxide, whatever it will generate after burning, this kind of, again, those lignocellulosic biomass can capture it for its own growth with the help of sun ray. And that's why it's a positive environmental properties. And we know that is that green plants are required for our own sustainable, our own existence. So that's why it has some positive environmental properties, and obviously it has some economic potential because of people who are living in they are not utilizing the high-end kind of technology. So, and they can easily implement one biorefinery in their own area, in the rural or the semi-rural area. They can easily make it, and finally it will be helpful for the those people, the rural peoples. So that's why it has a huge amount of economic potential too. So what's our target? Target is the first of all the biomass from the forest land, or the biomass from the agricultural land, or other secondary and tertiary biomass from agriculture and forest land. So the blue one, this kind of biomass we will get it, like it is the important ones, the MSW, or the municipal solid waste. This municipal solid waste we will get it from the urban areas. Again, it depends on what kind of biomass will generate, or what kind of waste they will they will generate, depending on the what kind of people they are living. So obviously it depends on the city to city, it depends on the area to area. So utilizing those kind of solid waste, also we can generate the bioenergy plant. And the left one, there is a biomass from the forest land. There is a in green color, it is showing that various kind of forest residues. We are also making it, depends on the fuel wood, even the other, let's say for other kind of, I mean, say the fruits, sometimes they are barks and those kind of thing also we can utilize it. Generally rural people, they can collect and they can utilize it for the burning. So instead of burning, that is the incomplete combustion, it will also create the pollution. So instead of doing that, we can teach them how to get a better amount of energy from that. So once we get it, easily it will create a huge amount of economic potential too. In the middle one, there is a biomass from the agricultural lands. So here our research lies, that agricultural land, instead of always cultivating those kind of feedstock, not only for the hours, but also we can cultivate some energy crops also. So from that energy crops, we can again differentiate into grain crops, oil crops, or the agricultural residues. Let's say for the after collection of our rice or the wheat, whatever the straw is left, that leftover straw we can utilize it for the biomass generation. It's a feedstock for the biomass, and from that biomass also we can always make a little bit fuel. Different kind of fuels we can make it depending on the type of biomass. So in the left hand side again, the petrochemical industry, I showed it from the crude is their feedstock, however is biorefinery, biomass will be the feedstock. Then it moves towards the down. So each time we're doing the cracking and refining, and we're getting the fine fuels, but with the petrol and diesel and the other petrochemical products, we're getting it. In each stage, we're collecting it. In the same concept, we can also utilize starting from the biomass. So tailored biomass, there's the biomass modification also, you can make it. Nothing but utilizing a little bit pyrolysis and gasification process. It's a very simple technology, you can do it. And also you can modify energy crops using some genetical engineering concept, that also you can make it. Once we make it, we can get some very green chemicals, like say for ethanol, methanol, butanol, lactic acid, those kind of thing. This is the primary material, and from there also you can make it the other products, like say for PLA nylons, fuel additives, solvents, resins. Those kind of products is almost equivalent to our intermediates, which will get it from the petrochemical industry. And finally, all these products you can utilize it for transport, textile, food, health, and other things. So depending on the type of biomass, again, we can classify it. So my topic is also working on the second generation biofuel. So apart from the second generation, I will start from the first generation biomass. What is the first generation biomass? And I will explain it why I pick up only the second generation biomass. So first generation biomass, basically the starch of molasses, ethanol, those kind of thing. And this kind of biomass basically compete with our food chain. That means if we're cultivating the maize, so maize is, from the maize we can get a huge amount of or good yield of ethanol and hydrogen. It's true, but it also competes with our food chain. So that's why it's sometimes where the demand of food is huge, in those kind of countries, they're supposed not to depend on the first generation biofuel. So we have to depend on the second generation biofuel. Second generation biofuel are those utilizing those kind of biomass, which is basically won't compete with our food chain, food or fodder in both cases. So at present, Brazil is working on the ethanol production. They are utilizing huge amount of sugarcane. But the same amount of sugarcane, if we are utilizing it, then our cost of the sugar and other material will increase, and that will create a huge problem. So India cannot be dependent on this kind of first generation biofuel. So that's why we can make our own biorefinery on the basis of second generation biofuel concept. So apart from the second generation, some third and fourth generation biofuels are also there. This third and fourth generation biofuel, basically it works on the algae. So this kind of biofuel still under the research, hardly will get any organization. Nowadays, Oil India is started to make a plant on the third and fourth generation biofuel in Guwahati. So still it is in research, hardly will get any good yield from this kind of product, because cultivation of algae is sometimes difficult and extracting the oil and other things are also there. It's in research, but soon this, I am sure that second generation biofuel will be replaced by third and fourth generation biofuel once those kind of technology will develop, but it takes a little bit much more time. So that's why in between second generation biofuel, we can emphasize it. We can simplify the technology so that technology can be easily transferred to rural people or some from the urban people also, so that they can implement their own area, this kind of biorefinery, and they will be independent, or I can say they will not depend too much on the conventional energy resources. So at present, ethanol, butanol, and mixed alcohols are present, and government of India already implemented that 5 to 10% we can do the blending. And instead of ethanol, if we go for the butanol, we can directly utilize for 80 to 85%. And in next coming days, we can make some mixed alcohol, that is mixture of butanol and other higher alcohol. So at that moment, we will be independent from the fossil fuel-based fuel. So blending at either refinery or blending at the retail is possible. And still, ethanol is much more important than the butanol, because butanol production is a little bit tougher, and hardly one or two organisms is producing. Most of them are Clostridium. They are a little bit pathogenic. And that's why handling of this microorganism and how we can discard it into the environment, that has some problem. Else butanol is the best candidate. So in overall, if we find it out, all the biofuel which can replace the fossil fuels, ethanol is a much more better candidate, because most of the case either we are utilizing yeast, if we can, and that yeast, whatever it will generate, that can also be utilized for other food production. So that's why ethanol is the best till date rather than butanol or other mixed alcohol. And this is the projection onto the second generation biofuel. As if I told you, 10 to 13% of the total transport fuel and in 2030, and by 26% it will be replaced by 2050. So if our technology is prepared for that, a huge amount of money as well as good amount of research can be going on this direction. And by 2050, that's why 90% biofuels will be on the cellulosic platform. And this cellulose will come in, and depending on the type of country, if it is not from the India, even throughout the world, depends on the type of cellulose, we can get it. For India, it will be obviously the second generation biofuel, the lignocellulosic format. And maybe the first world countries, they can produce the ethanol from that cellulose will coming from their first generation, that is either from the sugarcane or from our maize. So that's why we focus on the second generation products only. So as I told you, the first generation ethanol produced from the starch waste, which is always compete with the other food crops. And ethanol as fuel can't be directly to replace petrol, as the hygroscopic nature, and it will obviously corrosive in nature. So that's why it may a little bit that entire life period of an engine will be lesser. So if we're utilizing second generation biofuel, that will be excellent substitute of the fossil fuel, and we can produce, if ethanol is excess, we can easily going for the ethylene and polyethylene kind of product, which is not possible if we are going for the butanol kind of production. So that is the format that biomass, if you are going it, if you are going for the fermentation, you can get either ethanol or butanol. So from the ethanol, the intermediate will be ethylene and you can make the polyethylene. And but for butanol, if we go in for the butylene and the polybutylene, but polybutylene has still some limited application rather than polyethylene. And if we are making the propanol, which is still under research, we can get a little bit much more good end products. So these are the apart from the ethanol, which will directly replace the biofuel. So if it is the excess amount, we can make it. How we can going for the other value-added green chemicals, that is that projection. So that is the traditional flow. I can say conventional or traditional way of making production of the ethanol. That is from if we are utilizing energy crop, if we are going for the pre-treatment. And after doing the saccharification is nothing but a enzymatic hydrolysis. We'll get glucose, and this glucose, if we concentrate it and doing the fermentation, we can get the ethanol after doing some downstream process. There is either membrane separation and something distillation is there. We can make it. So there is a traditional way. So in the present way, we are also working on this part that if we remove that enzyme business, because the enzyme is very costly matter. Easily we can make a biochemical route where after doing the crushing, we can do the chemical hydrolysis, and whatever the C5 or C6 sugar will get it, we can go for the fermentation process and we can get the downstream. After doing the downstream, we can get the ethanol. And the moment we are doing the chemical hydrolysis, we'll also get some value-added products. So these value-added products, it will be a little bit difficult from the traditional, because in traditional one, people are still depending on the enzymatic hydrolysis. But it's not that this conventional flow is, it will yield much more better ethanol or another product other than the present one. Yeah, this one. But again, we are working also this how to improve the enzymatic hydrolysis process or reducing the cost of enzyme in the same route, so that we'll get a much more better yield. And utilizing both C5 and C6 sugars, because when we are doing the fermentation, very few species are there which can utilize the C5 sugar. Most of the organisms, they will utilize C6 sugar, and C5 sugar is basically left. So we have to find few other organisms which will produce C5 sugars and some other value-added green chemicals rather than the ethanol also. So here, this diagram, if you have looked in, the red color is the bottlenecks and how we can improve it, that is replacing by the green colors. So in red color, I have shown it that volatile or irregular supply of the feedstock, that is a major drawback for second generation biofuel production. So instead of that, if we make a dedicated energy crop and technology to composite with a range of feedstock, then this kind of problem is solved. So as I told you, in Medak district also, people are working on this sugar sorghum production. When I was in Nagarjuna fertilizer, I have seen it. Even the Maharashtra region, they are also emphasizing on this sweet sorghum production. Even some genetically modified crops, they are doing it. ICRISAT is also working on this kind of energy crop production. So even the northern region, almost it is that's rice straw or the wheat straw. After cultivating that kind of rice or wheat, they are basically throwing it out. So and what they will dump it, they have to burn it. So this burning will create the pollution. So if we can collect it in a sustainable manner, we can easily utilize it for energy production. And if you go to the northern side and further southern side, there is Kerala region, we get a huge amount of areca nut husk. I have worked on this. I will show it in my later slide, how we can improve it utilizing that husk for production of a little bit green chemicals and biofuels. So the second drawback is the expensive and slow enzyme-based sugar platform. As I told you, enzymes are costly as well as a slow process. So that's why it will increase the cost of the production. So technology will come that low enzyme loading and non-enzymatic process. So non-enzymatic process is purely chemical process. And you know that each chemical process, if we are much more emphasizing, then problem is that it will also create some hazardous product. That means whatever when the product is, our process is complete, how we can discard this product will be a little bit difficult. So that's why we're always working on the low enzyme loading and a faster rate of production. The third drawback is the inefficient or slow fermentation process. Obviously, the for ethanol fermentation process will take almost 5 days. So if we can cut it, so that's why novel organism having equal preference for C5 or C6 sugar. So that is a working with the pure biotechnologies. They are working on that. So if an organism is there which can utilize both C5 and C6 sugar, so our yield will be more, and as well as also we can improve the process in terms of reducing the entire time of operation. That is, instead of 5 days, if we can produce the ethanol within 1 or 2 days, it will be much more cost efficient, and the final product cost will be lesser. And the last one is the energy intensive downstream processing. You know that downstream processing of ethanol is costly because the distillation process sometimes it forms a azeotrope, and we cannot remove or we cannot extract the 100% pure ethanol from that, and it also demands energy. Wherever we are producing some kind of thing which will be from after burning those kind of thing, we will get some energy. So to get that product, if we utilize more energy, then the entire process will be failed. So that's why we have to improve a little bit newer kind of technology, which is required low energy process. So membrane-based separation processes, people are working on that. Even we have also worked on that. That in that separation process, once we get the fermented broth, which has some ethanol or butanol, how we can separate it easily without going to the process of distillation. So there is a low energy process invention. So these are the drawbacks, and these are the implementation, means how we can improve those kind. So we are working on the sugar platform. So first we have started with the biomass processing, followed by the pre-treatment, saccharification, that is enzymatic hydrolysis, and then concentration. So those kind of things only I will discuss today. So this is the first part, that is lignocellulosic biomass. If we collect it, we're going for the pre-treatment. Pre-treatment is nothing, it's a very energy intensive process. It will sizing the biomasses, and different kind of pre-treatment process exist: acid pre-treatment, lime pre-treatment, ultrasonic lime pre-treatment. So each step I will explain it, and what is the process scope of improvement, whatever I have done also, that also I will explain a little bit. So first, whenever we collect any kind of biomass, we have to go for screening process, and that's why it is called the characterization of biomass sample. So a few important characterization is required, which will show you whether the particular biomass is suitable candidate for the this biofuel production or not. That so those kind of analysis like physical characterization, chemical characterization, or its structural components, have to find it out. So in physical characterization, we have to among these all the part, the ash content is very important. If the biomass contain huge amount of ash is nothing but the minerals which biomass used to consume from the soil. So if ash content is more, that is not a suitable candidate for a biofuel production or in the biorefinery. Reason is that this ash or these minerals, we cannot utilize it. It will only reduce the yield of final production. Whereas the calorific value is important. If the biomass contain huge amount of carbon, the calorific value will be more, and that kind of biomass will be much more suitable candidate. XRD is basically crystallography. So if the biomass is much more amorphous, then enzymatic process will be much more smoother, and with less amount of time, putting less amount of energy, we can get a huge amount of monomers. That is, from cellulose, when you hydrolyze it, we get the glucose. So that part will be a little bit easier. And from TGA, there is a thermogravimetric analysis. We can find it out how much lignin is present, how much cellulose or how much hemicellulose polymers are present. And apart from that, if any other polymers is added on that also you can easily find it out. So apart from the CHNO2 analysis, there is carbon, hydrogen, nitrogen, sulfur, and oxygen, and the FTIR to find out what the kind of bonding is present. So those kind of things we have to find out from the chemical characterization process. And this biomass structural components, it is very obvious that if a biomass contain good amount of carbon, that this carbon and this volatile matter, this and the fixed carbon, this is directly related with the cellulose, hemicellulose, and lignin and extractives. So first we will go for the physical characterization. If we get a good amount of volatile matter or the fixed carbon, or the TGA result is also positive, or CHNSO is also for the carbon component is huge high, then we will go for the biomass structural component, that how much cellulose, hemicellulose, lignin, and extractive is there. Among that, if our technology exists that we can utilize more amount of, we can utilize the cellulose and hemicellulose, we will choose that. And if we find that okay, lignin content is more, that kind of biomass is not suitable for bioethanol or biofuel production, directly you can utilize it for other purpose, let's say for gasification or pyrolysis kind of technology to yield different kind of product, different kind of green chemicals. And if it is a huge amount of extractives are the other kind of elements. It's basically green chemicals, sometimes wax and other, sometimes so many medicines are also, you can get it in the extractives. So those kind of things will get it from the biomass structural components. So another chemical characterization important part is the sulfur content. If sulfur content is more or the oxygen content is more, that is also not a good candidate for biorefinery, because if sulfur content is more, then chances there it will form SOx gas, or sulfur dioxide or sulfur trioxide gas after burning. So this biomass, this kind of gas will be, it will be problematic in terms of pollution it will create, and it will be sometimes, I can say it will also create health problems. So biomass should have less amount of sulfur content and high amount of carbon content. So that is our purpose. And if oxygen content is more, then the calorific value will be less. So we should look on this matter. Next. So this is the picture from the Demirbaş. I took it, that what is the cellulose structure. There is a beta-1 for link, straight chain polymers are there. And this is a hemicellulose. This is a polymer of both glucose and some pentose sugar. Pentose sugar again depends on two types. Either it will be arabinose or the xylose. So if arabinose and xylose, again depends on type of plant we are choosing, or kind of biomass we are choosing. It depends on that part. And then it comes to the lignin. Basically, it's a polymer of synapyl alcohol, coniferyl alcohol, and synapyl alcohol. And this is a unique for each plant. So we cannot predict that what kind of polymer it is, what concentration of fumaryl, synapyl, or this coniferyl alcohol is present. It is unique for each kind of biomass, and each biomass will be different. So that's why if we characterize the lignin using, especially we're utilizing FTR for that, we can make a tailor-made kind of product for this purpose. So it's a structure of little bit, I will emphasize it. You can find it out how the straight chain links are there and the hydrogen bonds are there. So when we're utilizing enzyme, so enzyme basically breaks this bond and we can get the glucose. That's the monomers. Same for the hemicellulose, we can make a different stream for the cellulose and hemicellulose. And this is a lignin. This is a picture from the Parkwood lignin. And this is a cellulose biomass component. As I told you, cellulose concentration for agricultural residue will get it around 43% in general. Let's say it's a general concept. And for woody crops, the cellulose content will be 45%, whereas lignin concentrated is high, almost 22%. But for agricultural residue, we'll get 17% kind of agricultural residue. And municipal solid waste, that is always depends on, as I told you, the city to city it will vary. So here is also will get a good amount of lignin, around 10%, but ash content is huge, that is almost 15%. Cellulose concentration will be 45%, and for herbaceous energy crops, let's say for those kind of, here will get a good amount of cellulose, 45%, but problem is that it contains huge amount of water, the herbaceous energy crops, and that's why the calorific value or the initial process, that is crushing and other part, will be a little bit difficult. So that's why people are much more emphasizing on this agricultural residue and the woody crops, where easily we can convert it into value-added products. So these are few composition. Among that, you can find it sugarcane, that's contained 33% almost cellulose, which is much more popular. Even few bamboo, which is present in the northeast region, that has a 45% cellulose. But again, bamboo have some other property, so it will also compete. It has some other property that means we can utilize the bamboo in other purposes also. Bamboo itself has some commercial value, so people are not interested to utilize bamboo as a feedstock for bioethanol production. But rice straw, which has a huge amount of cellulose and less amount of lignin, but it contains almost 10 to 12% of ash content. So sometimes it happens that rice straw, we cannot utilize it for bioethanol production, depend on the area where cultivation is going on. But again, rice and wheat, both the two things are good candidate. But as if it contains huge amount of ash, it's not sometimes we are not able to utilize it for a biofuel feedstock. So these three biomass I have worked on. One is Bonbogori, areca nut husk, mose, and some groundnut shell. So Bonbogori, areca nut husk, and mose, these three things are available in your northeast region. And this groundnut shell, it is almost pan India, you can available it even in this winter season. People are consuming it like anything. So I have worked on this. So as I told you, the initial characterization and after doing the pre-treatment process, I found it that this is a crystal. A good crystal, you can find it out. There is before treatment, it looks like that way. So if I put enzyme here, hardly will get good yield. But if you do the pre-treatment process, that's why we make a amorphous kind of cellulose here. You will find it how it will, it will be meshed and water will be consumed, and finally it will be helpful for enzymatic hydrolysis process. So this is the proximate and ultimate analysis. These three biomass I have showed it here. That arecanut has contain 2% of ash, whereas these two Bonbogori and moose contain less amount of ash. So in this perspective, we can say that Bonbogori and moose will be act as a nice feedstock for biofuel production. And this is the carbon content, 41%, whereas it will be 54 and 52. And you can say the fixed carbon, it is also less. But volatile carbon is much more present in arecanut has 82%. So that's why it means it contains a good amount of hemicellulose content also. So this is the extractive. Extractive means we are doing some, that polar kind of solvent if you are using. Polar generally fetch the polar kind of material, and non-polar kind of solvent if you are using it, it will fetch the non-polar kind of material. So hexane, ethanol, and water extract people use to do it, and also find out the amount of cellulose, hemicellulose, and lignin content. And that's why we will also do it and find out that hexane content extract, that is a much more polar content is present in case of Bonbogori. And ethanol extract, if we find it, that is also more. And in water extract, that content arecanut is a little bit almost similar to this moose, and arecanut is same, almost 6% and 7.61%. So it means that the non-polar content of product present in its outer layer will be more rather than its polar kind of bio. So how to get it? So that's why we are working on this pre-treatment process. So pre-treatment process, I will explain the acid pre-treatment process is a traditional one. Now it has some own advantage and disadvantage, and followed by lime. And here I have improved a little bit. There is the ultrasound assisted lime pre-treatment. I'll explain it. So this is the raw biomass. If I go for the pre-treatment process, and pre-treatment process basically make it three kind of stream. So lignin, cellulose, and hemicellulose. You will get a three different kind of stream, and that is the major goal of the part any pre-treatment process. So if I little bit explain it here, so lignin, hemicellulose, and cellulose, that is a major any biomass you will get these things, and a good amount of good pre-treatment process using acid pre-treatment process. Let's say that is a traditional and established process. We'll get different kind of amount of sugar, and this hemicellulose part also you can remove it because and it looks like a red kind of color, but it is not efficient to remove the lignin and cellulose content. So that's why we have to put some enzyme to again extract the cellulose content in terms of glucose. So in good pre-treatment or ideal pre-treatment process, it has some objective, like for it will produce some amorphous cellulose, it will obviously reduce some byproducts formation like furfural. So if I use in acid, that is a major drawback for acid pre-treatment process also. It will produce huge amount of furfural, which basically acts as the inhibitory component for the microorganism. So that's why growth of microorganism will be stopped. And preserve the hemicellulose fraction. As I told you that hemicellulose has also some commercial value, although all the microorganism cannot digest it, those pentose sugars, but this pentose sugar also have some value. We can produce some xylose sugar or the xylitol for an artificial sweetener. So that can also can make it. So that's why ideal pre-treatment process will always preserve the hemicellulose fraction. And obviously it is required, less energy requirement is required because we have to put some energy to disintegrate this biomass. So if we are doing such kind of thing, then it will be a little bit difficult if you utilize huge amount of energy. So next one is the consumption of the less chemicals. So each enzyme and each pre-treatment process utilizing some chemicals. So if we are utilizing some chemicals, and consumption will be more, that will not a good pre-treatment process. So that's why another part is the reducing the cost of feedstock size. So you know that less the amount of feedstock size, higher the good the efficiency of any kind of reaction. So if you can ideal pre-treatment process, it does not bother that. It's the ideal case, but we have to reduce the feedstock to get a good amount of yield or good amount of further downstream processes. So these are the different kind of pre-treatment process. These are the chemical pre-treatment process, which is always established method. We are using acid, alkali, gas, some solvent extraction process and the ammonia explosion process. And if you're going for the physical pretreatment process, which is shown in the extreme left, this milling, basically we are utilizing it for our size reduction, different kind of mills we are using it. So each miller consume huge amount of energy. So that's why the ideal pretreatment process, suppose not to bother this kind of size reduction. There is the ideal case, but still we are using milling or crushing to reduce the size. Apart from that, some irradiation, that is the gamma wave or the microwave also you can utilize it. And the thermochemical process like pyrolysis and high pressure pretreatment process also you can do it. So this either physical or chemical pretreatment process, both this pretreatment process utilizing energy and maybe a little bit hazardous. Whereas biological pretreatment process is less hazardous. It does not require huge amount of temperature or pressure, or a good amount of chemical is not required. But the major drawback of biological pretreatment, which are basically done by either the fungi or the enzyme, problem is that slow process. The process is slow, it takes a huge amount of time. So if we can overcome it, this biological pretreatment process will always be dominant than any other kind of pretreatment process. So this is one of the non-hazardous chemical pretreatment process, is the lime pretreatment process. I have done using the Mohs, Ericanut and Ponbogori, and I can get almost the delignification ratio. There is almost 0.5. That means 50% lignin we are able to remove it, but the time takes almost 8 weeks. So 8 weeks is almost 2 months. So 2 months time I have to spend it to remove the 50% of lignin. So how to reduce it? So I have done it I have incorporated one ultrasound pretreatment process including this. So one ultrasound gun, if I put it using the same lime pretreatment process, same lime if you are utilizing it. So instead of 8 weeks of operation, I can get the 20% almost lignin percentage remaining. That is almost 50 to 60% lignin I can remove it. Within that, I can say this is enzymatic process. Within 8 to 10 minutes, I can do it, because the ultrasound process has a tendency to create some local heating, or the cavitation process is going on. So I can get a huge amount of temperature and pressure using this kind of ultrasound pretreatment process. And after doing this ultrasound assisted pretreatment process, we have also done putting some little bit of enzyme. So within 48 hours, I can get the 4.5% of glucose concentration. So if I solely using lime pretreatment, won't give that much of yield within that short span of time. So apart from this lime pretreatment process, I can also utilize some organosol pretreatment process, that is using some organic solvent, let's say for butanol and other higher alcohol also you can utilize it for the organosol pretreatment process. This organic solvent basically reducing the ether bonds. And if I'm increasing the heat little bit, it will act as a catalyst. So one kind of acid catalyst or the low, if I'm reducing the pH will also reduce, and finally this organic solvent will break down all these ether bonds and ester bonds, and we'll get again the good yield. So I have done this using this groundnut, and from this groundnut shell, and you can easily from this FDN analysis you can find it out how the breakage are possible in each portion of the lignin. So lignin is basically then entire lignin will coming out with that organic solvent, and beauty of the organic solvent is that if you extract that, the purification or the recycle of this organic solvent is a little bit easier. So then it comes to the simultaneous saccharification and fermentation. So earlier people used to do the saccharification in a separate way and fermentation in a different way, as I also showed it, that within 48 hours in this result, I've showed it that I have done the enzymatic hydrolysis. It's a sole saccharification process. So instead of doing that, I can, the saccharification and fermentation, you can combine this step. This will not only reduce the time, but also reduce the cost of the production. So two kind of reactor we have used it. One is a traditional continuous stirred tank reactor, and another is a fluidized bed bioreactor. So this is the actual enzymatic hydrolysis process. So how we used to do it, the cellulose enzyme will come and it will finally break it, and the glucose, and this glucose will consumed by the bacteria, and bacteria or yeast. And if hemicellulose sugar it can utilize, it's good. If else that hemicellulose we can utilize in a different way, and that yeast will finally produce some ethanol or whatever the biofuel is supposed to get. So this is a result from simultaneous saccharification and fermentation. And you can easily find it out that these three biomass, Ericanut, Haas, Bondogori, and Mohs, that with that 100 hours time operation, that time we are now working on how to reduce that much of amount of time. So within 100 hours, we can find it out around 4 to 4.5% we can get the ethanol with a good amount of yeast cell count, and also sugar consumption will be almost 0.1 to 0.2% for all kind of biomass we have made it. So now the research is still going on. Instead of 100 hours, how we can reduce it. Let's say for within a very less amount of time, how we can get the product that 3.5 to 4% ethanol. That's the threshold for any yeast cell in normal case. That how we can make it. So research is going on. That is we have also tried it for genetically modified engineering. So in the doing that engineering, easily you can that yeast can withstand up to 10% of ethanol concentration also. But problem is the survival of the yeast. So that we are lagging a little bit. So this is one part, and that is the schematic diagram whatever I discussed now. The spontaneous start tank reactor and fluidized bed bioreactor. This is a concept of a fluidized bed bioreactor. So here, instead of using traditional yeast and yeast, we are utilizing some, I can say this is a little bit organic loading route. There is nothing but a extract where we'll get it to the wastewater plant. So which for production of both fluidized bed bioreactor. The beauty of fluidized bioreactor is that this concept of agitation, we can easily reduce the cost of agitation, because the moment we are doing the fluidization, so entire this a good homogeneous mixture is possible during the fluidization, and easily you can collect the hydrogen gas as well as the ethanol also when we again go to the downstream process. So we compare this kind of things, and these are traditional CST here. So in any publication, people are also aware that we have to go compare with the traditional way how we can improve it. And I can report it that almost 20 to 30% more yield we can get it for the fluidized bed bioreactor. And during this operation, we also find it out that pH and pH has a huge amount of role for the hydrogen gas production, and also the temperature. So temperature, if it is less little bit, and if it's little bit, when it will go to the little bit higher, sometime something happened during this season. If we're using this by bacteria, the ethanol will be lesser, but the hydrogen production will be certainly it will going higher. Chances there maybe some methanogenic bacteria is present in that case, so that's why it happens. We are able to put production from this bone bogody, that biomass, using simultaneous ethanol and hydrogen production, and we have find the biohydrogen yield from 0.21 mol to 30.8 millimole of respectively for ethanol, and this is your hydrogen production. And apart from that, also some ammonia fiber explosion treatment is also there, and ionic liquid pretreatment. The problem of the ionic liquid pretreatment is that the separation of the ionic liquid, and it's a very costly affair. So we are also working on that, how to reduce that cost, and a low cost ionic liquid, if it is possible, then the cellulose we can easily dissolve in that ionic liquid. And ammonia fiber, the beauty of ammonia fiber is that the lignin is completely dissolved in that ammonia. But the problem is that if ammonia leakage is there, it is very difficult to handle. And same kind of problem also I have faced it in Nagarjuna fertilizer when I worked it in 2006. So that kind of problem is huge. But to be frank, it produces a good amount of biomass, which has a less amount of lignin, and this kind of biomass is very easy to digest it. The beauty of ammonia is that easily you can make it gas and liquid just by increasing or decreasing the pressure. So as I told you, we can also put that xylose, whatever the pentose sugar we are getting it, we can also pretreat it, and we can make some production of xylose from the pretreated husk of the areca nut. And from that xylose also we can go in for the xylitol, and xylitol act as a artificial sweetener, whatever the chewing gum and people are consuming this kind of good, rather than utilizing some chemical sweetener, we can easily replace those chemical sweetener utilizing this xylitol. So these are the few other chemicals, so the portfolio I can say, how we can do it from the biomass to sugar or lignin. So apart from this hydrogen and aromatic acid or sugar alcohol, we can get it this organic acid, because if any refinery cannot survive only producing this alcohol, they have to produce some other products also. So variety of product, if you are able to make it, then whatever the traditional refinery at present is there, like say for Indian Oil, HPCL and other things, soon they will convert into the biomass based refinery. So these are cellulose based fuels, whatever that we can make it using the levulinic acid, and from the levulinic acid we can make the succinic acid, and still we are working on the algae. So how to get this succinic acid and this kind of monomers and other industrial solvent, we can make it. So still research is going on. These are the aromatics, we are able to produce it from the petroleum. from the benzene, I have showed it how the adipic acid, the phenol, and the catechol. This is a very high value commercial products. You can make it. And the same kind of thing we can using from the glucose, xylose, or the glycerol or the arabinose, depending on the type of biomass you can make it. So that's all about my journey from the 2006 to 2020, and I hope I will also contribute something. So that's it. I will stop my presentation here. So if anyone have any question on this, so kindly ask me.
Yeah, yes, sir. Thank you, sir.
Thank you.
Yeah, can we start the questions?
Sure.
Yeah, I request Mr. Fahim to take the questioning.
Good afternoon, sir.
Good afternoon.
Sir, there is a question from Uday Bhaskar, sir.
Okay.
What are the aspects to be considered with regard to design of biofuels refinery based on source of biomass?
Again, as I told you, as I explained you also, that any other sustainable development, is there any possibility? Is it written in the chat? That question?
Sorry, sir.
Can you just explain, repeat
What
that question?
are the aspects to be considered with regard to design a biofuel refinery based on source of biomass?
Okay. This is again based on biomass. If our biomass is much more content, xylose content of biomass, then we're supposed not to go for the ethanol kind of thing. We have to produce the other sweetener and other green chemicals kind of production. If our biomass contain huge amount of, let's say for ash content, or which will basically generate that tar, then we suppose not to go for again for the this biochemical route. We have to go for the gasification or pyrolysis part. And if your biomass is a good amount of cellulose or hemicellulose content, directly we can go for the fermentation. So cellulosic biomasses, traditional fermentation process, you can utilize yeast. And if we would like to produce, let's say for a good amount of mixture of cellulose and our glucose and our hexose pentose sugars is also there, we can also able to make some butanol using some Clostridium species. And some PKR species also you can utilize it if our biomass has a good amount of hemicellulose is there. So that's why type of biomass we can easily change the technology as well as the pre-treatment process also. If it is a huge amount of lignin, we're supposed to go for the I can say the lime pre-treatment process. If it is contain less amount of lignin, we can easily utilize it for we can replace it with like acid pre-treatment process, and that's how way. Means the technology will differ, depends on what kind of feedstock we're supposed to get it. And that's why in urban areas, it is a little bit problematic to handling the municipal solid waste, because if it changes too much, then we suppose not to implement it. But still, some work is going on to produce some biofuel and other things. Even in Delhi region, in Delhi Haryana border, where all the garbage are means the municipal solid waste are generated. So they are also making biofuel plant into that place. Depend on the solid waste is present. So here you will find some plastic kind of solid waste. So they are using some gasification technology there to produce some syngas, and finally they are getting some chemicals from that. So the second question
from Uday Bhaskar, sir.
Yeah.
What is the status of octanol as a biofuel? Can it be better
yes,
than ethanol?
Yes. Earlier ethanol means in 2001, 2, or 4, when we are always dealing with that pollution is going on due to incorporation of catalyst in the bioethanol. So that late kind of catalyst, people are utilizing it for a good smoothing of the octane number to make the smoother octane number. So people are replacing those kind of lead-based material to the ethanol. So it's they're replacing the catalyst. Now we are replacing the entire fuel. We are going for the ethanol. So in near days, we can make it the octanol. The higher the alcohol it is, the less chances that it will be hygroscopic nature. So still ethanol capture huge amount of water, so which may not suitable for the longer kind of storage. Even it will harm the engines also. So if you can make the octanol and those kind of things, it will always be good.
Sir, can you stop the sharing, sir?
Okay, I can stop the sharing. Is it okay now?
Yes.
Yeah.
Sir,
Is there a
fine.
possibility of, yeah, ma'am.
Yeah, one more question from the chat box from Dr. Hemlata.
Yes, ma'am.
Yeah.
What is the procedure should be followed for the synthesis of aromatic compounds from xylose? Is it possible to synthesize in our laboratory?
Laboratory, obviously, it is possible with the academician or scientist basically working on this kind of small amount of chemicals and to produce a good amount. To be frank, it is only for the publication kind of thing. But the same thing when we are going for the industrial level, as if I told you, I also worked in Hyderabad in that region. So I have seen it, how much difficulties we are facing it to get a good amount of yield, because in laboratory you can make a hardly milligram kind of case, milligram amount. When the industrial level is supposed to go for the kilogram level. So that's the difficulties there to making the reactor. A simple case for the lactic acid production, I can say. In laboratory, it's a little bit easier. Same thing when we try to implement in a more industrial level, that heat amount, whatever it is generated, that is handling is a little bit sometimes difficult. So that kind of a problem, that is obviously an engineering problem and easily you can sort it out. So we can do it.
Question from Pawan sir. What is the possibility of considering macroalgae as potential feedstock for the bioethanol production? Any input on the vascularization of lignin to useful chemical? Please comment.
Just let me read it. Possibility of considering microalgae as a potential feedstock for bioethanol production. Yes. If the particular algae, as I told you, that third generation or fourth generation biofuel, we are working on that to genetically modify the algae also. The major problem of algae is its growth. It is not growing as fast as we think. Means cultivation in algae either in pond is little bit faster, but doing it needs a huge amount of land also. So that is the problem. But once we get that algae, if it does not contain good amount of, it is not contain the oil, then we can easily utilize it. And people are working on that to make it that amount of biomass. But cultivating or gathering that much of biomass sometimes difficult. Else it is a very good candidate for production of the bioethanol. And any inputs of valorization of lignin in use, obviously from lignin, as I told you, that's why I shared my screen also. So many chemicals from the levulinic acid, perfural also you can produce it, HMF also you can produce it. Even few my scholars are nowadays working on production of this lignin to other value-added chemicals, especially from the perfural derivatives, we can make it.
One more question, sir, from Pawan sir. Can utilization of xylose will improve bioethanol productivity?
Yes, Candida picia species, as I told you, they can only utilize that xylose, they can make it from the ethanol. But it's my personal opinion that don't go for that xylose itself as some commercial value. So instead of utilizing it for ethanol, which is a low value than those xylitol and other chemicals, no need to go from the xylose to ethanol. Rather than you can utilize xylose for other value-added chemicals, it will be much more better option.
Thank you.
Actually, sir, Dr. Prasad Jalade has joined, sir, today's session. He is good friend of Dr. Tiwari, sir.
Okay.
Good afternoon, sir, Dr. Prasad. Sir, can you hear us, sir?
Yes, Dr. Vanitha, thank you for bringing me up here. So nice to meet you all, and I'm enjoying Dr. Soumya's presentation.
Soumya Sasmal, sir, yes.
Thank you, sir.
Actually, Dr. Tiwari is not there, sir, in the meeting right now.
Okay. So is there any other question?
Possibility of starch storage, and there would be effect of natural green cover.
Welcome, Dr. Prasad, to this August gathering.
The development of biofuel.
Yeah. Can you repeat the question, Mr. Fahim?
Is there a possibility of starch storage by could affect the nature's green cover? Any other sustainable development issues included in the development of biofuels?
Yes,
It
yes,
is
yes.
in the chat by Uday.
That's all. That's why I told you it depends on what kind of means the motto of that nation. If it is a one kind of utilizing starch for production of biofuel or the green chemicals, it's a first generation concept. Only this kind of utilizing starch as a source of feedstock, it can afford only by the first world countries, not the countries like us where people are starving for food. So that's the major thing. We can utilize it for the research part. Obviously, it is always true. But for commercial purpose, I can say it's not a suitable option to utilize starch.
One request is there in the YouTube chat to share the PPT of aromatic.
Okay.
So I think aromatics from renewable.
Okay.
This is with the questioning session, sir.
Fine, just wait for a few minutes. Dr. Tiwari? Sir?
Yes, I am here. I am here.
Yeah. Dr. Prasad has joined, sir.
Good morning, Dr. Prasad. How are you?
Good morning, Dr. Tiwari ji. I am doing fine. How are you?
I am fine. Just now I have finished my class. Today is the last class for this semester.
Wonderful. Nice to see you all. And I met our old friend Pawan ji also online today. Very exciting.
Yes. Yeah.
Prasad garu, namaste. How are you?
See,
I'm doing fine, sir. Thank you so much. Nice to see you again here.
You are in India now?
Yes, I'm in Hyderabad.
So should I close it or should I transfer the thing to the host
No,
position?
sir. Like, just wait for 1 minute, sir, for vote of thanks.
Okay.
Actually, Fahim is having network problem, so
Good afternoon, sir. Am I audible, sir?
Yes, Fahim, you are audible.
Yeah. A very good afternoon for the respected dignitaries, principals, faculty, delegates, and my dear students from various colleges across India. Myself, MD Fahimuddin, Assistant Professor, Department of Pharmacology, VIPER. I feel it as a pleasure and immense happiness for me to give a vote of thanks for proposing for the day of 4 for the FDP and SDP session on recent advances in science and technology. On behalf of VIPER, I would like to thank Dr. Soumya Sesmal sir for delivering a fantastic lecture on current and future trends in second generation bioethanol production. Thank you, sir. We are very grateful to you and hope to see you in such programs in future also. And we seek your guidance for such project work, as we are, our NSS team also is working in the same parallel direction. And I would like to thank our management for trusting us and always embrace us to conduct such events. I thank my principal, Dr. A. Ramesh, chairman of this event, who always behind us and motivate us for doing such programs. Thanks to Dr. O.N. Tiwari sir, the principal scientist IARI, New Delhi, the co-chairperson of this FDP program, who has motivated our faculty and has made this successful. I extend my thanks to Dr. K. Vanitha ma'am, HOD Pharmaceutics, who is the convener of this FDP program, and the coordinator and organizing team members of VIPER, who has scheduled it and made it happen. Thank you to the Dr. Dinesh Mohan sir, Associate Professor, Pharmaceutics Department, for giving a nice introduction for the speaker. Last but not the least, I am thankful for all the networking and supporting team of VIPER, who has played a major role for the successful conduction and smooth running of the online session. Thank you for the faculty, delegates, and students of VIPER and various organizations who have participated with their total zeal and enthusiasm in this FDP program and made this a grand success. The feedback link for the session is being shared in the comment section. Please leave your feedback. And with a hope to see you all in the afternoon session, which is going to be at 2 p.m. by the lecture by Dr. Biswat Bunia sir. With same zeal and enthusiasm, I would like more participation in this session in the afternoon. Thank you.
Thank you, sir. Thank you, Vanessa. Thank you, sir.